Let's be blunt. The old rulebooks for automotive functional safety, they're obsolete. We're in the era of the software-defined vehicle now, and that means we need a whole new playbook. So today, we're going to do a strategic deep dive into the massive shifts happening right now and what it all means for how we engineer cars today.
And you know, we really can't overstate the urgency here. We're in the middle of a software explosion. The lines of code in a single car, we're talking hundreds of millions now. This isn't just a small step. It's a complete revolution, and it's pushed our traditional, hardware-focused safety methods right to their breaking point. The bottom line is, what worked yesterday just doesn't cut it for the cars we're building today or tomorrow.
So, all this pressure, it brings us to the core idea of our analysis today. We're in the middle of a massive paradigm shift. Functional safety is no longer about just ticking boxes on a compliance checklist for individual parts. No, it's become a fundamental, first principles problem of system-level architecture.
So here's the key takeaway. The one thing you need to remember. Safety has to be engineered at the system level, not the component level. And this new reality? It's being driven by two huge paradigm shifts and a whole universe of standards that are starting to overlap. This creates a brand new strategic framework for all of us. Let's break down the evidence.
All right, let's tackle the first big shift. This one comes from a world we all know pretty well, the world of microcontrollers. For years, the industry kind of operated under this powerful myth, a myth that's become pretty dangerous now, the myth of the safe component.
And this, right here, illustrates the problem perfectly. If you're building a simple shed, sure, you can probably get away with just stacking up some really strong bricks. But a modern car's electronics architecture isn't a shed, it's a skyscraper. And its safety, its stability, that depends on the architectural blueprint, on the system engineering, not just on how strong each individual brick is. So just grabbing a bunch of parts certified to ASIL D, the highest level, doesn't automatically give you an ASIL D system, not even close.
And why is that? It's because safety is what we call an emergent property. It's not something that lives inside the components themselves. It emerges from this incredibly complex web of interactions between all the parts. And this is the critical thing, the specific context they're operating in. You take a component out of the context it was designed for, and poof, all those safety guarantees are off the table.
If you want the definitive case study on this, look no further than the Ariane 5 rocket failure. Back in '96, this rocket just blew up 37 seconds after it launched. And the cause? A piece of navigation software that was proven, certified, and totally safe on the Ariane 4 rocket. It was just reused. But the Ariane 5 had a different flight path, a new context. That change caused a data overflow, which led to a catastrophic failure. It is the ultimate and most expensive lesson. Context determines safety, not the component certificate.
Okay, so that brings us to our second huge shift. Now we're moving into the world of high-performance computers, the ones running massive, complex, open-source software. You know, like Linux. And this is where the challenge gets even tougher. I mean, you can't possibly certify the entire Linux kernel, right? So how in the world do you use it safely?
Well, the answer lies in this really brilliant architectural pattern. The best way to think about it is like a trapeze artist with a safety net. So the Linux application, that's your trapeze artist. It's performing these incredible, complex, high-flying functions. We don't even try to certify every single flip and twist the artist makes. Instead, we use a hypervisor to create a safe platform. And right below, we place an ASIL-certified safety monitor. That's our safety net. It's just constantly watching, ready to catch the artist and make sure we get to a safe state if anything goes wrong.
So the technical term for this is ASIL/QM decomposition. It's really just a strategy of intelligent separation. You've got your complex, quality managed, or QM part, that's the trapeze artist, and you've got your highly reliable ASIL-rated part, the safety net. And the goal of that ASIL monitor isn't to make Linux perfect. Let's be clear about that. Its only job is to make sure that even when Linux fails, and it will, it can never ever cause an unacceptable risk to the vehicle.
And let's be really clear about why this is the only path that makes sense. Trying to fully certify a huge, constantly changing open source project like the Linux kernel, it's just a dead-end road, both commercially and technically. You'd be totally cut off from all the amazing updates from the open source community, it would take a monumental reverse engineering effort, and frankly, it would be financially impossible. Decomposition lets you have the best of both worlds. You get all the innovation of open source without ever compromising on safety.
So we've walked through the two big paradigm shifts, but the picture is getting even bigger. Functional safety, or FUSA, the stuff governed by ISO 20262, well, it's no longer the only game in town. We're now dealing with a convergence, a coming together of multiple safety and security fields that are all interconnected.
This table really lays out the new landscape for us.
So alongside ISO 26262, FUSA, which deals with system faults, we now have ISO 21448, which is for safety of the intended functionality, or SOTIF. This covers those tricky cases where the system is working exactly as designed, but it's still not good enough for the situation, like a sensor being blinded by sun glare. Then you've got AI safety, which has to tackle the fuzzy, probabilistic nature of machine learning, and holding it all together, cybersecurity. A truly safe vehicle today absolutely has to address this entire landscape.
And all of this is happening at a blistering pace. Get this, Volkswagen's China-specific architecture was developed in just 18 months. Think about that. For a legacy OEM, that kind of speed is it's unheard of. This extreme compression of our development timelines puts an unbelievable amount of pressure on our safety processes. It demands that we use these more efficient, architecture-driven approaches.
So, let's bring this all together. What does this all mean for you, for the engineers actually doing the work? We can boil all of these strategic shifts down into a final section, an actionable playbook for this new software-defined era, and it's built on 4 core principles. First and foremost, think in systems, not components. Your focus has to shift away from the certification sticker on an individual part and onto the integrity of the whole system architecture. Remember, safety is all about context and interaction.
Principle number 2, isolate. Don't certify everything. You have to use these architectural patterns like ASIL/QM decomposition to manage complexity in a smart way. The goal is to build intelligent safety nets, not to try and certify every single move the trapeze artist makes. That's how you unlock innovation without getting stuck in certification hell.
Number 3, design safety in, don't add it on. This is huge. Safety is not a feature you can just bolt on at the end of the project. It has to be a foundational part of your thinking from day one, embedded deep in your architecture. Trying to retrofit safety later? It's expensive, it's ineffective, and honestly, it often means you have to tear everything down and start over.
And finally, our 4th principle, embrace the convergence of standards. Real safety assurance today requires a holistic approach. We have to create a single, cohesive safety case that seamlessly integrates functional safety, SOTIF, AI safety, and cybersecurity. They can't live in silos anymore.
This playbook gives us the framework we need to build safe vehicles right now. But it also points to the next great challenge. Because as the software in our cars becomes more intelligent, more predictive, more human-like, it leaves us all facing a final, crucial question. How are we going to redefine what it even means for a vehicle to be safe?